Hi everyone, I'm Samara and today I'm going to explain how Kirchhoff's loophole and current conservation predict what really happens in simple DC and RC circuits. Using the phys circuit construction kit, I built virtual versions of common lab setups like series resistors, ideal meters, and an RC network. I checked calculated currents and voltages against the simulator and then explored how resistance changes a capacitor's charging time. By the end, we can see how both the power and the limit of the ideal model. So for some of the so for the introduction, this is what we used. For some of the key and fundamental concepts, these ideas basically drive everything that we measure. First, the Kirchhoff's voltage law, which is the algebraic sum of all the potential differences around any closed loop is zero. Then we have Ohm's law, which says that a resistor drops voltage in proportion to current, so delta V is equal to IR. The capacitor basics, delta V is equal to Q divided by C, with equivalent series and parallel rules that mirror resistors but flipped. And these rules basically turn every circuit picture into simple algebra that we can test. Now, for some of the assumptions and calculations, before collecting data, I made three big assumptions. One was that wires and meters are ideal, zero resistance for wires, infinite for voltmeters. And then for two, batteries hold a perfect 1.5 volt or 9 volt with no internal resistance. And then the resistors and capacitors are perfectly ohmic and loss free. Under these conditions, our calculations should match the simulator exactly, and any mismatch would highlight where real world physics, is actually used. Now, for the series circuit charge and current conservation, our first test loop has two 1.5 volt batteries for a total of 3 volts, a 47 ohm and a 100 ohm resistor in series, and 2 ammeters. And the resistances are 147 ohm, divide 3 volt by that, and we predict 0.02 amps everywhere in the loop. Both meters read plus 0.02A, and if I flip the leads on the top meter, it reads minus 0.02A, which is the same magnitude, opposite sign. That's basically Kirchhoff's law. Current entering any point equals the current leaving. Now for the voltmeter swap, I pulled out the top ammeter and dropped in a voltmeter across an open gap. Because an ideal voltmeter has enormous resistance, it breaks the circuit. The current will fall to zero, exactly what the bottom ammeter shows, but the voltmeter still sees the full battery EMF, which is 3 volts, which proves that potential differences can exist even when no charges are moving. Then walking the loop with a voltmeter, I then touch the probe sequentially around the label points A through H, and the readings are from A to B, it was plus 3 volts, B to C was 0 volts, C to D was negative 0.96 volts, D to E was 0 volts, E to F was negative 2.04 volts, F to G was 0 volts, and G to H was 0 volts as well. And then adding them algebraically, and then they cancel to zero, which is another clean win for the loop rule. And then there's drops across the 47 and 100 ohm resistors, which share the same 1:2 ratio as their resistances. Now for the RC circuit, to give it some memory, I replace the resistors with a light bulb filament that acts as a 10 ohm resistor plus a 0.2 farad capacitor and a 9 volt battery. With 10 ohms in the loop, the bulb glows for about 15 seconds while the capacitor charges and then fades over another 15 as it discharges. Doubling the resistance to 20 ohms stretches both intervals to roughly 26 to 27 seconds, and a higher R means a larger time constant, so everything basically slows down. Now to quantify T, I ran one more trial with a 30 ohm bulb and the same 0.2 F capacitor. The ideal model predicts T is equal to 6 seconds, but fitting the exponential discharge in the virtual simulation gave 4.6 seconds. So what really is the problem with this? There's basically two ideal errors. One is that the simulation is ideal, but the manual stopwatch clicks were not. Human reaction time easily shifts a 5-second window by half a second. And then two could be that the bulb's resistance rises as it heats, so the true R during discharge is lower than 30 ohms, which would shrink T. In the physical lab, we'd also see the lead resistance, battery, and capacitor leakage. So in conclusion, across all the tests, Kirchhoff's rules reliably predicted voltages and currents as long as our ideal assumptions held. But the RC experiments highlighted how resistance controls charging speed and how real world factors like temperature, timing error, and non ideal components shift results away from textbook values.